We analyze a lot of flights. Here's what crashing planes have in common. Every time a plane crash makes the news, the same question comes up. Was there a warning sign? Something hidden in the data? Something we missed? This video is about understanding whether unusual flight behavior tends to appear before things go wrong. By turning flight paths, speeds, and altitudes into measurable signals, we can treat flights like time series and ask an important question. What behavior looks unusual compared to normal flights? We will walk through one real example, show where abnormal patterns appear, and explain what these signals really mean. We will now start with our first chapter. Automatic Dependent Surveillance Broadcast, or ADS-B, is a system used to track aircraft in real time. Most modern planes continuously broadcast their position, altitude, speed, and other flight data over radio signals. Anyone with a simple ADS-B receiver on the ground can pick up these transmissions. With an inexpensive setup like a Raspberry Pi and a basic antenna, you can receive signals from aircraft tens or even hundreds of kilometers away. Thousands of volunteers around the world collect these ADS-B data and share it online, but access to large historical datasets is often restricted or requires registration. That's what makes ADS-B.log interesting. The project publishes a free dataset on the previous day's flight traces to GitHub, updated daily, created by Katia Esposito. So let's move on with our second chapter. When you're trying to identify an aircraft, there are three key identifiers that matter, and once you understand them, everything starts to make sense. First, there's the registration number, also known as the tail number. That's the legal identity painted on the aircraft, like a license plate on a car. The second piece is the ICAO 24-bit address, also called the hex code. This is the signal the aircraft sent, and it's also used to track the aircraft in real time. You can think of it as a digital ID. Both the tail number and the hex code can change during an aircraft's lifetime. That's why the third identifier is so important. The MSZ, or manufacturer's serial number. It's like the aircraft's fingerprint. It never changes and uniquely identifies the airframe throughout its entire life. While the MSZ identifies the aircraft itself, the registration and hex code are what's used in daily operations and tracking. For our use case, the hex code and the MSN were all we needed. It is time for our next chapter. So, how do we detect problems in flight data today? What is state of the art? For this, we reference the academic paper from Basoro et al. With the title, Recent Advances in Anomaly Detection Methods Applied to Aviation. Traditional methods were simple. Airlines set fixed limits, like if the speed goes above X during landing, flag it. Pretty straightforward, but it only catches problems you already knew existed. Modern approaches go further. Instead of predefined routes, they learn what a normal flight looks like across hundreds of parameters and flag anything that doesn't fit. That means catching issues outside these predefined routes. The paper covers some powerful deep learning models for this. But here is the thing, these deep learning models are data hungry, and you only had trace data from 2023 onwards, fewer than 200 flights in total. So, deep learning simply wasn't our first choice. Instead, we went with an approach that Basoro et al. Also covered, K-nearest neighbor. The idea is straightforward. Every flight gets compared to its closest neighbors in the future space. If a flight looks very different from all the others around it, it stands out as an anomaly. We aggregated the flight data over a 20-minute window, then extracted physical features like acceleration or curvature, plus statistical features like the mean, skewness, frequency features, and more. We then use K-nearest neighbor to classify accident flights against the learned distribution of normal ones. Alright guys, before we jump into training our model, we need to talk about the data first and how we will clean it. Because no matter how good your model is, if your data is messy, your results will be too. And in our case, we are dealing with real flight tracking data, which means missing values are basically guaranteed. But first, let's quickly look at what we are actually working with. What you see here are real-time flight tracking records, essentially a digital trail of a flight. We have position data like longitude and altitude, movement data like ground speed and vertical rate, plus some metadata. Now, here is our approach. We handle missing values on a per flight basis using different methods depending on the feature. The key thing is that we never interpolate across different flights, only within the same trajectory, as mixing flights would create completely unrealistic data points. The first question we have to ask ourselves is, how many data points are actually missing? Here you can see the missing values in total and in percentage. We drop columns with over 50% missing values. At that point, they are not viable as features. Now we have to think of good strategies on how we can replace these missing values. Before doing anything, we like to plot a correlation matrix of our features. Correlation tells us how strong two variables move together. And if we look at our matrix, two things immediately jump out. First, altitude and altitude geometric have a correlation of basically 1, which makes total sense because they are measuring the exact same thing. Second, both of them strongly correlate with ground speed, around 0.88. That's because aircraft typically fly faster at higher altitudes, and vice versa. And this is actually super useful for us. It directly shapes how we're going to handle missing values for these columns. If altitude is missing, we can fall back on altitude geometric and vice versa. And ground speed gives us a reliable hint about the aircraft's state on the ground. We will start by cleaning up ground speed, because this column will help us clean a lot of the others later on, so it's important to get it right first. For this we use linear interpolation. The idea is simple. If a value is missing between two known values, we just draw a straight line between them and fill in the gap. Here you can see an example from one of our actual flights. Now, as you can imagine, the full cleaning process was pretty long. We have a lot of features, each with their own challenges. Showing every single step would go way beyond the scope of this video. So if you want to see the complete cleaning pipeline for every feature, check out our notebooks on GitHub, linked in the description. Alright, let's move on to the next chapter. Now that our dataset is clean, the next step is to explore it and uncover insights that will guide the design of our classification model. Let's start with density maps of our 186,000 flight accidents concentrated in North America and Europe, with smaller hotspots in Japan and Australia. The non-accident map looks similar, so we're really just seeing where a flight gets recorded. Empty regions like Central Asia, Africa, and the oceans probably reflect sparse ADS-B ground receiver coverage. To get a better feel for what our data actually looks like, let's walk through the features of our dataset using a simple example flight. We have latitude and longitude, which simply track where the plane is. Altitude and altitude geometric both capture how high the aircraft is flying. Ground speed tells us how fast it's moving. Track degrees show the direction it's heading. And vertical rate tells us whether it's climbing or descending. And when we look at all of them together, we can clearly see the takeoff, a steady cruise, and then the landing. Let's take a look at one of the accident flights in our dataset. This is WOPAS Flight 2283. On August 9, 2024, this ATR 72 was on a routine flight from Cascavel to Sao Paulo in Brazil. The crash was the deadliest aviation accident in Brazil since July 2007, killing 62 people on board unfortunately. According to the report, the aircraft lost speed, triggered a stall warning, and entered a flat spin, completing 5 full rotations before hitting the ground. This is the type of accident our model is trying to detect. Now let's see what this flight actually looked like in our data. We start with the altitude column. Altitude looks more or less constant until we reach the accident time. Here we see a change in the color of our values, meaning the altitude decreases abruptly. Let's look at another metric highlighted in the crash report, namely the drag degrees. The report said the airplane entered a flat spin. On the map, we can see that our values represent these spins, as they take on the different colors of the 360-degree range at crash time. Now that you know better what the features mean, please have a look again at our feature plot from before. The time series should tell a much clearer story now. We will now come to a very interesting part of the video, namely the pre-processing. With our data explored, the final step before modeling is pre-processing. We will match aircraft types between classes, downsample in an accident flight, resample the time series and derive some extra features. Let's start with aircraft types. Different aircraft exhibit substantially different flight characteristics, including speed, altitude profiles, and maneuvering dynamics. If the aircraft type distributions differ between the two classes, the model may learn to distinguish aircraft types rather than identify accident-related behavior. Let's look at the distribution of our two classes. A distribution simply shows how often each category appears in the dataset. For example, what percentage of flights are A320s, B737s, and so on. Here you can see the final distribution after our stratification process. Both look very similar, which is exactly what we wanted. We also reduced our large non-accident dataset down to 2,000 flights, since a strong imbalance with our limited accident flights would make classification unnecessarily difficult. The next step is to resample our data. Right now, some flights have data points every second, others every 10 seconds. It's all over the place. Our aim is that all flights have the same temporal resolution, so the model sees comparable sequences regardless of the original sample rate. To do this, we need a good target sampling rate. In this image, you can see the sampling rate distribution of the raw dataset. Both classes show a bimodal distribution. The first peak, around 2 to 4 seconds, likely corresponds to low altitude phases, like approach or landing, where many ground-based ADS-B receivers are in range. The second dominant peak sits around 20 seconds, typically of cruise phases where fewer receivers are available. Let's investigate 2 flights where the plane dropped the most potential crash sites. For the altitude, all sampling intervals capture most of the information easily. For vertical rate, shorter intervals capture more detail, although the difference is not too extreme. Nevertheless, we choose 5 seconds, a good trade-off between detail and data size. If you're curious about the exact interpolation strategies we used, feel free to check out our notebook linked in the description. Let's move on to the next chapter. Let's talk about the derived signals we used in our model. On top of the raw traces data from adsb.lol, we also feed in the 4 derived signals, all computed from the original data. Acceleration captures how quickly the aircraft is speeding up or slowing down along its flight path. Vertical acceleration does the same thing in the vertical direction. How fast the aircraft is gaining or losing climb rate. Turn rate tells us how fast the heading is changing. Basically, how aggressively the aircraft is rotating about its vertical axis. Curvature describes how sharp the flight path itself is. Think of a hairpin. The tighter the bend, the higher the curvature. Together, these signals add information that prior papers found useful for detecting abnormal behavior. Now to the model. The idea behind car nearest neighbor is simple. Every flight becomes a single point in a feature space, described by a list of numbers. One feature might be the mean altitude, another the maximum ground speed, and so on. But why do we use aggregated features instead of feeding the raw time series directly? The raw data for one flight is an entire table, with hundreds of rows, one per time step. KNN Model expects each row to be one flight and each column to be a feature. Keeping the raw time series would mean flattening each flight into thousands of features. A very high dimensional space, which is problematic for distance-based models like KNN Model. Instead, we summarize each time series into statistics like mean, maximum, and variance, ending up with 132 features per flight, which we later reduce to the most informative ones. To look even deeper into the behavior of a flight, we use the fast Fourier transformation, FFT for short. Here is the idea. Imagine 3 sine waves, each oscillating at its own frequency. When combined, they create one complex, messy-looking signal. FFT untangles exactly that. It breaks the signal back into its individual components. Each spike you see on the right represents one of those original sine waves. Its position tells you the frequency, and its height tells you how strong the oscillation is. From the frequency view, we can extract 4 additional features per signal. The dominant frequency tells us which oscillation pattern is strongest in the signal, essentially what the signal beats to most strongly. We can see that for vertical acceleration and turn rate, accident flights cluster at lower dominant frequencies than normal flights, indicating slower period oscillations in these signals during abnormal operation. Spectral energy is the total power in the spectrum, the signal's overall strength or variability. Spectral entropy measures how the energy is distributed across frequencies. Concentrated in a few frequencies means a regular structured signal. Spread across many means a more complex, unpredictable one. And finally, the low versus high frequency energy ratio splits the spectrum in half, asking how much of the signal comes from slow, smooth changes versus fast, sudden ones. Across some features, accident flights tend to separate from normal ones in their distribution, a potentially useful pattern for a model. Time for the main event. We will now put KNN neighbors to work on our flight data and see whether a simple distance-based model can separate accident flights from normal ones. So, how does a pipeline work? It's a chain of steps. First, the data. We split our flights into 3 sets. The training set is where the model learns and gets tuned. Tuning means finding the model's best settings, like how many neighbors a flight should look at or how we measure distance. Instead of guessing, we try many combinations and keep what works best. To judge each one thoroughly, we use cross-validation. Testing just once can be lag. Maybe that slice of flight was easy. So we split the training data into several slices, test on each turn and average. A setting that scores well across all of them is genuinely good. The validation set is a separate independent check. Does a tuned model hold up on flight it wasn't tuned on? And the test set stays untouched until the very end. These are brand new flights the model has never seen. The predictions here are the ones that count, as close as we get to the real world. Next, scaling. KNN Model measures how far apart 2 flights are, but altitude runs into the thousands of feet, while turn rate are in degrees. So we put every feature on the same scale, otherwise the big numbers would drown out the simple ones just for being bigger. Then the features themselves. Each flight comes with 132 numbers, but not all of them earn their place. Some carry signal, others are just noise. So we score each feature by how clearly it separates the accident from normal flights, using neutral information, and keep only the strongest. And since this runs fresh inside every cross-validation fold, the flights we are testing on never influence which features we pick. Here we can see features which were selected by our model. One last issue, our data is heavily unbalanced. Accident flights are rare, so our flight's nearest neighbors are almost always normal, and the model drifts towards calling everything normal. To fix this, we use Smooth. It generates new synthetic accident flights that resemble the real ones, evening out the balance so the model gets enough accident examples to learn from. And in parallel, we run a few Ableton studies, running the pipeline over and over, each time changing just one thing: the sample rate, the time window, the derived features, or the smooth balancing, to see what actually moved the needle. Here are the results. On the unseen dataset, the model held up impressively. It caught 26 of the 32 accident flights, with just 3 false alarms out of 400 normal ones. For a simple distance-based model, separating accidents from normal flights this cleanly is a strong result. And of everything we tried, SMOT made the biggest difference. On its own, it lifted the model from 20 core to 24. With the tuning on top, we reached 26, almost halving the missed accidents compared to where we started, at the cost of just 1 extra false alarm. For accident detection, where catching the rare cases is the whole point, that was our biggest step up. So, to wrap it up, overall, we are happy with how the model performed. For a simple distance-based approach, separating accident flights from the normal ones, this cleanly is a solid result. Out of all the features we engineered, a few clear signal groups stand out. The attitude profile was central. Its extremes, its breadth, and its overall shape showed up again and again. Another strong group was spectral energy of the frequency domain, which measures the total power of a signal. So features like vertical rate, spectral energy really reflect how strong and pronounced the overall motion is. It lines up with the picture that the sheer magnitude and intensity of the flight's movement in vertical rate, turn rate, or acceleration carried a lot of weight. That said, it's worth being honest about the limits. Our data was scarce. Reliable accident flights only go back to 2023, so we were working with a fairly small set of real accidents. We made the most of what we had, but more data would almost certainly help. And there's one clear elephant in the room: the weather. We couldn't bring in weather data for this project, even though conditions like wind or storms are obviously tied to many accidents. Adding that would be a promising next step, and probably where the biggest improvement is still waiting.